All right, this is the second hour of for Physics 1B 1376 section. Okay, so let's look at some applications of the continuity equations. The continuity equation tells us that the quantity of area times velocity is going to be a constant, which means when the area gets small, the velocity has to get big to compensate, which is the idea that if I have a nozzle on a hose, the water will flow faster out the smaller opening, something that you're all pretty familiar with. So let's look at this equation right here. Flow of an incompressible fluid. I guess we can bring this over here because we might need it. All right, so incompressible oil with a density of 850 kilogram per meter cubed is pumped through a cylindrical pipe, at a rate of 9.5 liters per second. The first section of pipe has a diameter of 8 centimeters. What is the flow speed of the oil? What is the mass flow rate? The second section of the pipe has a diameter of 4 centimeters. What are the flow speed and mass flow rate in that section? Say something if you want me to make the text larger. I'm going to start drawing a picture. You should start trying to solve the problem while I draw it. Okay. 8 and 4. Okay, so we have this tube that's shaped something like this. It has liquid, was it oil that's flowing through it? We use red for oil. So we've got this fluid, it's flowing through here. And what we know is that the first section of the pipe has a diameter of 8 centimeters, so this is 8 cm. The second section has the diameter that's 4 centimeters. So this is 4 centimeters. There's fluid flowing through here, and the rate at which the fluid is flowing, we don't know, but we do know the density of the oil is 850 kilogram per meter cubed. And we also know that it says it's pumped through a cylindrical pipe at a rate of 9.5 liters per second. What is that going to be? What is the 9.5 liters per second going to be? dV/dt, that's right. That's the volume flow rate because it's in liters per second. So I'm just going to label that as dV/dt. So volume over time, that is 9.5 liters per second. We will probably have to convert that into... The symbol for liter is a capital L, in case you haven't seen that before. I suspect you probably have, but I don't know. All right, so that's all we know. And in part A, it asks us, it says the first section has a pipe, has a diameter of 8 centimeters. What is the flow speed of the oil? So flow speed of the oil would be the velocity, right? So I'm just going to label in here that the velocity at this point, we're going to call V1. And then when the water flows out, or the liquid flows, the oil flows out over here, we'll call the velocity V2. And since this section is smaller, V2 should be bigger than V1. So In part 1, part A, what is the flow speed of the oil? What is its mass flow rate? It's talking about the first section. So we're going to want to find the flow speed. What is V1? And the mass flow rate. The mass flow rate is, well, it's this. It's rho dV dt. That's what the mass flow rate is. As you can see in the top right. Right, mass flow rate. You take the density, you multiply by the volume flow rate, that gives you the mass flow rate. Because after all, density times volume gives you mass. So, what do we do for part A? How do you solve for V1? What do I need to do? How do I find the velocity of the fluid right here? Divide by the area. Get the area and divide by, yeah, that's right. Yeah, okay. So according to this equation right here, volume flow rate, A times V, area times velocity, is equal to dV dt. So what I'm going to do is, I'm going to call the area on the left-hand side over here, we'll call this one A1. We'll call the area over here A2. And if we do that, then what we know is, as you all are saying, that A1 times V1 should be equal to the volume flow rate, which we're given. So that means that we can solve for V1 by taking dV dt and just dividing by the area. So V1 should be equal to, dV dt is 9.5 liters per second. We divide that by A1. The area over here, A1, I'll just write this off to the side here, area should be equal to pi times the radius squared, or pi times the diameter divided by 2 squared. So we're given diameter, which is 8. So our area is going to be pi times 0.04 meters squared. We're doing half of the diameter here for the area. Now, can I just go ahead and calculate it from this, or do I need to do anything else? Convert liters to meters cubed, that's right. So we're going to multiply here by a conversion factor that will allow us to convert from liters into meters cubed. So when I draw a conversion factor and I want to get rid of liters, the first thing I'm going to do is I'm just going to write 1 liter down here. And then I'm going to try to figure out how many meters cubed are there in a liter. And I believe the answer is there are 0.001 meters cubed in a liter. Scoot down just a little bit. And someone could look that up, but the way that I remember this, actually probably someone should look it up in case I made a mistake. The way I remember this is that 1 liter is a box that is 1 decimeter on each side, a cube that's 1 decimeter on each side. So that's 0.1 times 0.1 times 0.1. Okay. This thing's kind of freezing a little bit here. I don't know what's going on, but okay. So what do you get if you calculate this out? Thanks for checking that. .9 UMM units? What? What's UMM? Oh, you meant meters per second? Yeah. Oh, you said 1.9 units. I see what you're saying. I get it. Okay. I read that as like micromillimeter or something. Okay, so 9.5, I got the same thing. I got 1.89 meters per second. That's what you get for V1. Not volume 1, but velocity 1. We also want to find the mass flow rate. Mass flow rate's pretty easy, because to find mass flow rate, you just do density, rho, times dv dt. Okay, so what should I write? Should I write, I'll just write mass flow rate. Oops. Could just say like MFR or something. So this is going to be equal to density times dv dt. So this is going to be the density of the fluid, which was 850. And then we multiply by dv dt, which was 9.5 liters per second. We do another conversion factor, 0.001 meters cubed per liter. And we get this should be about 8 kilograms per second. So I got 8.1 kilograms per second. The meters cubed cancels out with the meters cubed. You're just left with kilograms per second. So that's our mass flow rate. You don't have any questions about that? Christian, I don't know. You can come up with your own if you want to. Like volume flow rate, you could put like VFR. Mass flow rate could be MFR. Yeah. I don't know if there's a symbol. Yeah, whatever you want to do. Okay, part B. The second section of the pipe has a diameter of 4 centimeters. What are the flow speed and mass flow rate in that section? Okay, let's figure that out. There's enough room over here that I think we can just write in this space, right? Let's just do it like this. We'll just say part B. So the question now is, what is the velocity as it flows out? Which I should have called V2. Maybe I pushed the undo key. Velocity 2 is what we're trying to calculate here. And this is where we can use the continuity equation that we derived, which tells us that the cross-sectional area A1 times its velocity there is equal to the cross-sectional area A2 times the fluid's velocity at that location. And since we've already found V1 right here, we can just say that V2 is going to be equal to the ratio of A1 over A2 multiplied by V1. And then we can now plug in for these areas here. So A1 is the area over here. We said that was going to be pi times the radius, which is half of 8 centimeters, or 0.04 meters squared, divided by A2, which is going to be pi times half of 4 is 0.02, so the radius is going to be 0.02 meters, also squared. And we just need to multiply that by 1.89. And if you look at this ratio right here, it's going to be basically, you don't even worry about the decimals, the pi's cancel. It's 4 squared over 2 squared, which is like 2 over 1 squared, which is 4. So our answer is basically going to be 4 times this. What's 4 times 19? It's probably pretty close to 80. It's probably 86 or something like that. So this is going to be something like 8.6 maybe? No, not 8.6. 3.6. Wait, 19 times 4. Yeah, 8. Wait, it can't be 8.6. It has to be like 7.6, right? 7.5, there we go. It's more like 7.6. And that's going to be meters per second. Yeah, 80 minus 4, not 90 minus 4. And what about the mass flow rate? Is that going to change? No, it's not, because look what we did to calculate it. We took the oil's density, we took the volume flow rate. The volume flow rate is constant, right? The volume flow rate's the same in both places. So yeah, the mass we'll use MFR is the same because it's constant, because we're talking about an incompressible fluid. And if it's not compressible, then the density is not going to change. If it was compressible, that would mean that as we squeeze it together in this section of the pipe right here, its density would go up. That's what a compressible fluid would do. The density would go up. But because it's incompressible, the density is not going to change, which means that the mass flow rate doesn't change either. And that's a very, very straightforward example of how you use the continuity equation. And we'll continue to use it in the next section of this lecture, where we talk about Bernoulli's equation, because we'll need it there too. Christian says, so the logic to it is that although the speed of the fluid is faster, because the opening is smaller, the same amount of fluid goes through per second. That's you nailed it. That's a very good conceptual explanation, Christian. Yes, exactly. Yeah, without using any math, you basically summarized all the things we said very well. I like that a lot. That's good. Because the opening is smaller and it's going faster, the same amount of fluid can flow through every second. Yep. Okay. Well, the next thing to talk about is Bernoulli's equation, I believe, unless I'm missing something. Nope. So before we even go into what the equation is, I want you all to think about something that hopefully you've experienced at some point in your life. Maybe, maybe not. I don't know. So here, we'll put this down at the bottom. And let me just describe a scenario. Okay, so I don't know how many of you drive cars. Maybe some of you do, maybe some of you don't. But you probably ride in cars, buses. Would this apply if you're riding on a bike? Probably not. You kind of have to be in some kind of a car for this to be true. So hopefully you've all experienced something like this before. And if you haven't, kind of try to look out for this in the future, because you probably will notice it. So suppose that I am sitting, trying to turn left at an intersection, right? So I've got an intersection right here. Here's the intersection. And I'm sitting here. Here, let me clean this up a little bit. So here's your intersection. You need to have more lanes. Okay. So here's the intersection, and here is the divider, and there are 2 lanes. So this is like the right lane over here has 2 lanes. Okay. So you've got cars are going to be coming in this direction, and you're sitting here trying to turn left. Okay. So you're sitting right here. This is you. Okay, I'm not going to write it on there, but this is you sitting right here, sitting in this car. And you want to make a left turn, right? But let's say that there's a green light right here. So in front of you is a green light. Is the red on top and the green on bottom? I never remember. I think it's red on bottom, regardless. So there's a light right here, and it's currently green. So you're trying to turn left, but you can't go left because there are oncoming cars, right? You can't go left because there are oncoming cars. So you're trying to turn left. Meanwhile, behind you, there are large cars that are coming. So let's say there is a large, like one of those like moving vans or something like that. And let's say that it's moving in this direction, okay? And it's moving pretty fast. Let's say that it has a velocity of, so you're on like city streets, so it can't be going that fast. Let's say it has a velocity of like 40 miles an hour though. Okay? And you're just sitting here, you're trying to go left, but you're sitting here, you're at rest. Okay? So this big truck this big moving van comes cruising along like this. Does the picture make sense to everyone? You're sitting at a stoplight, you're trying to turn left, cars are coming into you, so you can't make the turn, so you're just sitting still, and there's a large moving van that's passing by right here. Does this situation seem familiar to you? Have you all experienced this at some point in your lives? You're sitting at a traffic light, you're trying to go left. Now, if you can think about this, and you can imagine this happening in your mind, maybe you could think back to when you've been in this scenario before, and you can tell me what you experience. What do you feel when that moving van rushes past you? What happens to your car? You feel a shake. The car shakes. Yep, the car will shake. It'll wobble back and forth for sure. Do you notice when the van moves towards you, if the car lurches towards the van or away from the van? Does your car start to shake by moving towards the van first or moving away from the van first? And what does your intuition tell you? What do you think happens? You all agree that your car shakes. You think away. Towards. Okay, so there's some disagreement. I like this. Towards. Towards, away. Okay. All right. So towards the van first. Okay. So it does seem like more people are saying towards than away. 1, 2, towards. Okay. Now, I actually don't know the answer to this question. Bernoulli's equation is going to tell us that it's towards. I think it's towards, but every time I'm sitting in this scenario, I'm always like watching to see if I can tell for myself. And I encourage you to do the same thing. Next time you're in a scenario like this, it doesn't have to be exactly the scenario. It could just be you're driving along a freeway and someone passes you really quickly on the left, right? It's the same exact idea, whether you're moving or sitting still, but you absolutely feel the car move, which means there must be some kind of a force that's happening. Would you all agree? Your car is not going to... It does have something kind of to do with the vacuum pad, yes, a little bit. So, just next time someone passes you really quickly, whether you're sitting still, whether you're driving down the freeway at 60 miles an hour and someone passes you at 90 or something like that, especially if it is a large van or something like that that has a big sidewall, right, a big flat sidewall, you'll notice that when the van passes you, that the car actually lurches towards the van as it passes by. And then, of course, it's going to start to shake, right? Because if it gets pulled closer to the van, now your car is going to have to go into like back to equilibrium. It's going to shake back and forth, right? Because the van takes away the air as it drives past you. Maybe. Let's see, Pat. Let's see after we talk about like the physics of what's going on with Bernoulli's equation. So the answer to what's happening here is in Bernoulli's equation. You tell me if you think if your explanation still makes sense after we do Bernoulli's equation. I think you might think it still makes sense. Okay, so let's look at what happens. Okay, so that's the first like thing that I think about when I think about Bernoulli's equations. I think about this scenario because it comes up a lot, especially in Los Angeles where we're driving a lot, that cars pass you very quickly. And Bernoulli's equation can describe why it is that your car shakes, okay? All right, so let's explain what Bernoulli's equation states. So Bernoulli's equation is almost like energy for fluids. And for this one, we're going to use a picture that I grabbed from another textbook because I think it's a nice picture. Right here. Come on. I just want to click on that. There we go. So Bernoulli's equation is going to look at what happens with fluid flowing through a pipe where the fluid can flow up. Okay? So we have fluid, and it's flowing in a pipe right here. Okay, and it's pretty similar to the picture we had before where the size of the opening here is called A1. So the area over here is A1. The area over here is A2. Again, we're still using all the same notation. Velocity 2 is the velocity of the fluid as it flows here, and velocity 1 is the velocity of the fluid that it flows here. The distinction between the other one is that now we have a height defined here. So because the fluid is going to, so this is a little partial of fluid. It's flowing in a pipe. It has a height y1 right here and has a height y2 right here. It's the same fluid, but it's like the fluid at one point is here, and then the fluid at another point is here. But it's the same pipe. This is like pipe at one point in time. This is the pipe at a later point in time. Okay. Now what you have in this pipe is basically a continuous flow of fluid. So fluid is flowing in this side and is flowing back out that side all the time. Okay. But we've just cut our pipe, and we're looking at a partial of fluid as it flows through here, all right? And in particular, we're going to look at the work done on the fluid. we're going to look at the fluid pressure created on this piece right here by the other parts of the fluid. So imagine fluid flowing through a pipe, right? And let me just draw a picture down here. You've got fluid, it's flowing through a pipe, right? And we're just saying, suppose we take a piece of our pipe right here and we look at just one little piece and the water that's flowing through it. So there's liquid flowing here, there's liquid flowing here, right? Now, the liquid from behind, would you agree, pushes on this, right? Liquid from behind is going to push on this piece of fluid. Would you all agree with that statement? If you don't understand, replace the fluid with a bunch of like balls. Like imagine that there's a bunch of balls in this pipe and we're pushing the ball through the pipe, right? Or like sand or something like that. If we look at one piece of it, then the fluid from behind has to push, right, forward on that little piece right there, right? But as the fluid from behind pushes, right, the fluid from the front pushes back. Does that make sense? And again, if thinking about it in terms of water doesn't make sense, replace it with sand and imagine that I've got something inside the sand. I try to push on the sand in the back, it pushes on the piece in the front, but then there's also sand in front of it, so it's going to push back on it. Does this make sense? Because the idea of what we're saying here is that there's work being done on this little parcel of fluid that we have right here. Here's our parcel of fluid in the picture. And the work is going to be done from behind. Okay? The work is going to be done from behind. So the pressure from the fluid behind it is going to push it through the tube. And what we're going to do is we're basically just going to say that the work done on the fluid is going to be the work that's done in section 1 over here on the left, plus the work that's done in section 2. How do we do work? Well, remember that work is equal to a force times a distance. Right? Work is equal to a force times a distance. And where's the force coming from in this case? In this case, that force is going to be coming from the pressure of the fluid times the area of the opening multiplied by the displacement that the fluid undergoes. That's what the work is going to be. Pressure times the area times the displacement of the fluid. So the work in section 1 then is going to be the pressure from behind times the area 1, P1A1, multiplied by the length of the fluid in this section, which is going to be delta x1. That's just the thickness of the fluid, the thickness of the thing. Before we called it ds1, now we're calling it delta x1. It's the same concept, just this thickness right here. And then I'm going to say minus P2A2 times delta x2. And that's because the fluid in front of this capsule right here is going to be pushing back on us when we get to this point. And that's why it's going to be negative. So positive work from behind, negative work from in front. Anyone have any questions so far? Do you all remember work? Remember work? Work is this thing that tends to kind of either increase or decrease the energy of a system, right? Friction can do work to decrease energy, right? You can push on an object to do work to increase its energy. So there's a connection between work and energy. And that connection is through the conservation of energy equation. So this would be the net work done. Would be this minus this. What's that equal to? Well, in Physics 1A, we learned that the work done by non-conservative forces acting on a system, right, is equal to the change in mechanical energy of the system, which you can write as change in kinetic energy plus change in potential energy. In case you don't remember what these symbols mean, K is kinetic energy. Remember, kinetic energy is like the 1/2 mv squared thing, mass times velocity squared. You probably all remember that. And U is potential energy. And potential energy could be like potential energy due to a spring. It could be the potential energy due to gravity. It could be the potential energy stored in an electric field if you happen to have taken 1C. In this case, it's just going to be gravity. This fluid, as it flows upwards, it has kinetic energy for sure, right? Because it has velocity. Anything that has velocity has kinetic energy. It's going to gain potential energy when it moves up some height, right? And potential energy is defined, at least close to the surface of the planet, as just mg times y. Right? So let's write out what this would be. We will say that this net work is going to be work done by non-conservative forces because the force of the fluid has to be a non-conservative force. If you don't remember, a conservative force is basically gravity, springs, and that's pretty much it. The electric force is also conservative. Anything else, like the fluid pressure in a pipe, is going to be a non-conservative force. So all of this stuff right here ends up going onto the left-hand side of our equation. Paste. There we go. All goes onto the left-hand side of our equation right there. That's the work done by non-conservative forces. All right. On the right-hand side of our equation, we know that the mass of our piece isn't going to change. So this mass here and the mass here are going to be the same. The only difference is going to be that it's going to occupy a wider area and a skinnier thickness. So when I describe the kinetic energy of this object, I'm going to write it like this. The change in kinetic energy should be 1/2 its mass times v2 squared minus v1 squared. That's the change in kinetic energy. v2 squared is its final speed. v1 was its initial speed. Plus, we also have to write m times g times y2 minus y1 because it changes height. And now we're going to do some things. What is A1 times delta x1 going to be equal to in this picture right here? Keeping in mind that A1 is the area of the end cap, delta x1 is this distance right here. What do you get when you take area times the distance if you have a cylinder? You get volume, right? So I'm going to say that the volume over here is V1. See, this is where it gets really hard because I have to use capital V1. V1, and we'll say the volume over here is going to be capital V2, which means that we can write... Oh, I forgot. Does the volume change? No, of course it doesn't. The volume's the same in both cases because that's what we're talking about. We're talking about these incompressible fluids. So it's the same volume in both cases. So we can write that... We'll just write it over here so that I make sure that I've written it down. The volume, in this case, is equal to A1 delta x1, but it's also equal to A2 delta x2 because we're kind of following the same piece of fluid as it goes through. So now we can write our equation like this. The left-hand side becomes P1 times V minus P2 times V equals, all this stuff doesn't change, so we'll just copy it down. And let's just look at this equation for a second before we write the next line. Okay, so the pressure at point 1 is P1. The pressure at point 2 is P2. This is the pressure from the rest of the water in our container. Now, the difference between those pressures times the volume is related to the change in energy of the system. This is a pretty interesting equation if you look at it. It basically says that the change in kinetic energy plus the change in potential energy of your fluid is going to be directly related to the pressures. The pressure at P1 and the pressure at P2. That seems to mean that pressure not only depends on depth, which we already knew, right? We already knew that pressure depended on depth. It also depends on velocity, the rate at which the fluid flows. And that shouldn't be too surprising to you because when you go into your shower, when you go in to take a shower and the water pressure is really low, when you say the water pressure is really low, what do you really mean? You go take a shower and you notice the water pressure is really low. What do you mean by that? When you say that the water pressure is low, when you go take a shower, what do you mean? What is it that you notice is true about the water coming out of the shower head if the water pressure is low? It's coming out slow. It's slow. It's slow. Yeah, not fast. It's slow, right? So you already know when you say water pressure is low, What you mean is that the water is moving slowly. But look, right here, there's a connection between pressure and velocity. So it's not that surprising. I mean, you already knew that. You're smart people. You knew that water pressure has something to do with speed, right? But this equation just kind of solidifies it. Now, the next thing we want to do is we want to get rid of mass. Because mass isn't super useful when you're talking about a fluid. Mass is the mass of a piece of the fluid. How are you going to find a piece of the fluid? And how are you going to agree with someone else on what piece of the fluid you decided to take out? That's not going to work very well. Instead, when we talk about fluids, instead of talking about mass, we talk about density, right? So what we're going to do is we're just going to divide the entire equation through by 1 over the volume. If we do that, then the volumes will cancel out on the left-hand side, and we'll just get P1 minus P2. And on the right-hand side, instead of M over V, we'll write rho. So this will become 1/2 density times V2 squared minus V1 squared plus M, and it becomes rho G Y2 minus Y1. This is basically Bernoulli's equation, but I'm going to rewrite it in a different way for you. We're going to put all the ones on the same side so that it looks like this. So it's going to be P1. V1 is negative over here. When I add it to the left-hand side, it'll be positive. So this is Bernoulli's equation. It's effectively conservation of energy for fluids. I mean, since it came from energy conservation. So this is what we call Bernoulli's equation. And it's often written in a slightly different form. Basically, if you look at the left and the right-hand side, they have all the same form except for these subscripts. So what you can do is you can just say the quantity of the, if I look at a fluid, the quantity of the pressure plus 1/2 density times velocity squared, this is basically its kinetic energy per volume, multiplied by rho G times the elevation, that this is a constant. And that is, when I think of Bernoulli's equation, this is what I think. The quantity pressure plus kinetic energy per unit volume plus potential energy per unit volume is a constant. Okay, it's a constant. And if we apply this to this picture right here, see if we can understand why this works the way that it does. Maybe this one's a little more complicated. Maybe it's not. I don't know. We think about what happens when this van gets to this point right here, right? When this van gets to this point right here. In particular, we think about just these two pieces. We think about just these two pieces here. Let me make them bigger so we can actually, we think about what's going on. So let's erase the stuff in the middle. And what I want you all to think about is the airflow in this case. So suppose that there is air flowing in front of you. Doesn't need to be, the air doesn't need to be flowing, but suppose that there's air that's flowing here, okay? There's airflow in this direction, right? What happens to the flow of that air when it gets between this little skinny portion right here? What happens to the airflow as it tries to squeeze into this area right here? What happens to the speed of the air? So I asked the question and no one was answering it. As soon as I said, what happens to the speed? People started typing. The speed increases. Pat will talk about the pushing in a second. But the speed is increased for sure, right? For sure, the velocity of the air inside of here, air speed goes up, right? So let's put 2 points in right here. So this is going to be point number 2, and this is going to be point number 1, okay? So out here you're going to have pressure P1, you're going to have velocity V1, right? And over here you're going to have, inside of here, you're going to have pressure 2, and the velocity is going to be V2. And as you all said, it's going to be faster. So V2 is like this, right? God, it just gets so messy when I draw too many lines. But here, we'll just put it like that, V2. Okay, So out here, velocity is slow, right? When we look at Bernoulli's equation right here, we're not even going to worry about y1 because the elevation is going to be the same in both cases. Do you all agree? Same elevation, all the air's on the ground, basically, right? So if the pressure out here and the velocity out here are related to each other, meaning that the quantity p plus 1/2 rho v squared has to be a constant, right? Then if v1 is slow and v2 is fast, what does that mean about the pressure? How do the pressures have to be comparing to each other? So in this case, if v1 is less than v2, what has to happen to the pressure? How are the pressures related? P2 has to be greater than P1? I don't think so. There's no way this would work if that's the case. P1 has to be... Oh, no, you're all right. Is it because I wrote this one wrong? V2 is greater than V1. Yeah, I got it right. This has to be this way. P2 is less than P1. I think you both wrote it backwards. Yeah, we're taking y equal to 0 because it's the ground. That's right. Yeah, we're saying y equal to 0 in both cases. So if the velocity increases, right, if this goes up, the pressure has to go down correspondingly, right? You all see what I mean? If this is to be a constant, if the velocity out here, it's probably easier if we pick numbers. I don't know if it's easier if we pick numbers or not. Point is that if the pressure, if the velocity goes up, the pressure has to go down. Put in a simpler way, high speed air or fast moving air exerts less pressure. High speed air exerts less pressure. If the velocity goes up, the pressure has to go down correspondingly, right? And so now you have a scenario where the pressure out here is P1, right? The pressure in here is P2, but pressure 2 is less than pressure 1, right? So what does that mean? That means that there's effectively almost like a vacuum in here, right? There's not really a vacuum, it's just lower, it's a lower pressure area. And so if you have high pressure out here and you have low pressure on the inside, then you're going to feel a force, right? You're going to feel a force that pushes you into the low pressure section, just like a vacuum would. You're going to get pushed in towards the car, and then the car is going to rattle back and forth. Now you can tell me yourself if this actually happens, but I think it does. The takeaway from this is this right here. High speed air exerts less pressure. Okay? And it's all because of Bernoulli's equation. That if it's the same air and the velocity increases, if the velocity goes up, the pressure has to go down. Yeah, low speed air exerts more pressure in this case, yeah. Exactly. I'll give you a couple other examples of this and how this works. And I'll show you this when we go to campus, but suppose that I take two large, like relatively heavy-ish balls, and we hang them from some kind of a support, okay? So they're just suspended, but there's a small gap in between them right here, okay? And then what we do is we take a high-pressure air nozzle. So we have an air nozzle. And we shoot high-pressure air through here. Okay? No, sorry, I'm saying it the wrong. It's high-pressure air, but the point is that it's moving really fast. You shoot really fast-moving air through here, okay? So the air that moves through here is very fast relative to the surroundings. What is going to happen to the balls? Are they going to swing together? Are they going to push apart? Or is nothing going to happen? What do you all think? Your intuition probably tells you that they should push apart. That's definitely what my intuition tells me. that if you were to do this, that they would push apart. But the reality is, and I'll show this to you on Wednesday, is that when you shoot air through here, because that air is moving very quickly, the pressure from the outside air is going to be greater, and they will actually come together and knock. And again, I'll show this to you when we go in the lab. I'll let you do it yourself. It is very, very surprising. If you happen to have at your home like a couple of cans, like they need to be kind of light, like aluminum cans. Like, so if you have like some Coke cans or Pepsi cans or something like that, or beer cans or whatever you got, and you can do a similar thing where what you have to do is you take 2 cans and you put them on a table. They've got to be relatively close together. Okay, so leave like a very small gap and get them to sit still on a table. And then above the top of it, blow air into here. So this is a person. Above the top, blow air in between them. And if you do it straight down and properly, they will, instead of flying apart, they will actually roll together. Does that make sense? They'll actually roll together. Oh, I can show you. I think I can show you a demo of this too, that you can do this yourself. So find a piece of paper of some kind. Here. Yeah, try that thing with the cans. You can try this too. I think I might need to make it smaller, but here's the demo of what you do here. Take a piece of paper. You can do this yourself right now. Like, grab a piece of paper. It doesn't matter what size it is. It can be like a small piece of paper from a notepad like this. You know, it can be a big piece of paper like this. I think this piece of paper should work. So here's what you do. I think if I go sideways, this should work the best, right? So let the paper fall down like this, right? And put your lips so that like your bottom lip is on top of the paper so you don't cheat. You don't want to blow underneath it. What I'm going to do is I'm going to blow across the top, okay? I'm going to blow straight this way. Watch what happens. I think this paper might be kind of heavy. We'll see what happens. Here we go. Do you all see that? So I'm not blowing underneath it. Obviously, if I blow underneath, it will easily pop up, right? The point is that when you blow on top of it, the same thing happens. There we go. It lifts up. And the reason why it lifts up is because as you blow air across the top right here, that is going to be fast-moving air. It's going to exert less pressure, and so the pressure from the atmosphere from below will push up on the thing and it'll lift it up. That's basically why an airplane flies. Like what you just saw right there, the fact that the paper lifts up like that is why an airplane flies. Because the air flowing over the top of the wing is faster than the air flowing over the bottom of the wing, and it creates lift due to the pressure difference. And that happens due to the way that the air wing is shaped. Another thing that I can show you when we come to class. I can show you a picture too if you want, but... So that is Bernoulli's equation. I'm simplifying it massively by saying that high-speed air exerts less pressure, but I mean, that's pretty much part of what it says. And that's one of the more impressive things about it. It's very surprising to me. I mean, even doing this now, it very much surprises me that when you blow across the top, the paper actually lifts up. Did any of you try it yourself? Were you able to get it to work? Yep, cool. I remember reading about this in a book when I was a kid. I had like some book of like science experiments that I found at the library. It was like supposed to be like things you can try at home and stuff like that. And there was this whole section on Bernoulli's principle. This is also called Bernoulli's principle sometimes. And there were all these little things they told you to do at home. And every time I tried them, I couldn't get them to work. But they didn't tell you to do this. This one you can get to work really easy. It was always telling me to do stuff like take a spool of thread and put something on the end and then blow on it. And you'll see how something gets stuck to it. And it just never worked for me. But, later in life, I got to actually see some of these demos. So I'll show you a lot of Bernoulli's demos when we go to campus on Wednesday. So it's a pretty cool idea. Do we have enough time to do problem? We sure do. We have 8 minutes, so we're going to do one problem. Alrighty. Not much time, so we will probably go through this relatively quickly. And we'll probably put numbers in too, because I hate doing these problems without numbers. I like it, but I know that it's not super great for you all. Speed of flux. So the figure shows a gasoline storage tank with a cross-sectional area A1 filled to a depth H. The space above the gasoline contains pressure P0 up here. And the gasoline flows out of the bottom of the tank through a short pipe with a cross-sectional area A2. We want to derive expressions for the flow speed in the pipe and the volume flow rate. Those are the two things that we want to find. The flow speed and the volume flow rate. So here's our gasoline tank, and it has a cross-sectional area A1 at the very top, a cross-sectional area A2 at the very bottom, and the fluid is flowing down like this. Now I'm going to give you these numbers as if it was given to you in a problem. So we're going to say that A2 is going to be, okay, let's say that the radius, let's call it R2. Let's say the radius of this, R2, is equal to 5 centimeters, okay? And let's say that the height H, so if it's a storage tank, it's got to be pretty big, right? What's 5 times 3 is 15? That's reasonable, right? 15 feet? Probably too much. Maybe like 3 meters is the height. And we want to find the flow speed and the volume flow rate out here. So let's say the flow speed here is just V2, okay? All right, I'm going to do this symbolically, and we'll throw some numbers in at the end, all right? The bottom of the tank is open to the atmosphere, by the way. And the pressure at the top is P0, okay? So we're actually going to need to know what this one is at some point. So we'll come up with a number for that. Let's say that P0 is equal to like 1.2 atmospheres. So it's pressurized tank, so it's kept at slightly above atmospheric pressure, and then it's open to the bottom. So the bottom down here is going to have atmospheric pressure. All right, so our Bernoulli equation tells us that P1 plus 1/2 rho V1 squared plus rho GY1 is equal to P2 plus. Since there are Y1s and Y2s in here, let's define some things. We'll call this Y2 and say it's equal to 0. And we'll call the top Y1 and say that it's equal to H. The pressure at the top is being called P sub 0. I hate the way that they do this in this book, where like they tell you that this is atmospheric pressure, but then look at the problem. This is atmospheric pressure down here. This book is very inconsistent with stuff like that. Maybe it went through multiple editions and they didn't change things. I don't really know. Pressure 2 is the pressure out here, so that's atmospheric pressure. Notice that the pressure that we're talking about here is the pressure external to it. So the external pressure here is P0. The external pressure down here is P atmosphere. It's not like you don't need to find the additional pressure due to the depth or anything like that. It's just about what's the external pressure acting on the fluid. So P0 up here is the pressure at the top of the tank, and P atmosphere is just that it's open to the atmosphere. One thing I will say is that quite often in problems, can I erase? I wonder if it'll let me erase the picture. I don't think it will. They won't tell you anything. They'll just say, these examples are always so much easier than the problems. In problems, if you see something and it says that it's open to the atmosphere, that means the pressure you're going to use is atmospheric pressure. Does that make sense? If it says something is open to the atmosphere, you're going to use atmospheric pressure. If the tank at the top was open, then they would both be atmospheric pressure here and here, okay? Just putting that out there. Something to keep in mind, because you're definitely going to have, as always in physics, you're going to have problems where they don't explicitly tell you all the information, right? So I'm just letting you know that that's what that means when it says it's open to the atmosphere. Yeah, actually, I think I already mentioned this because it also comes up in the statics problems. But I'm just reiterating it here. If it says it's open to the atmosphere, use atmospheric pressure. Okay. That's not the case here, but now our goal was to find V2, right? So V2 is the thing that we want to find. This variable is what we want to find. Now, we in principle will have a lot of information here, right? So what I'm going to do is I'm going to move all the information that we don't know to the right-hand side and leave everything else on the left-hand side, okay? So we're probably going to know... Here, let me draw a line right here to indicate this is not part of the... We probably know the pressure, right? I'm giving you the pressure over here. So P naught minus P atmosphere. Those are going to be knowns. We are also going to know, oh, look, y2 is equal to 0, right? So we can just set that equal to 0. So then we have plus rho g y1. And then we'll move everything else to the right-hand side. So that's going to be 1/2 rho v2 squared minus 1/2 rho v1 squared. Because v2 and v1 are going to be things that we don't know. Now, another thing that I'm going to tell you is very often in these type of problems, they are not going to tell you the area at the top, and they will not tell you the velocity at the top. They'll just tell you that the opening at the bottom is really small. And, oh my god, there's a big spider walking across my wall. They'll tell you that the opening is really small, and you're going to have to make the assumption that the fluid flow rate at the top is going to be 0. Does that make sense? A lot of the time, you're going to have to make the assumption that the velocity v1 is 0. And they're not going to tell you that. They're just going to assume you understand that. So, in this case, we're not going to do that, but just letting you know. Sometimes you have to make that assumption that v1 is going to be really small. In this case, though, if v2 and v1 are both unknowns, how could we... Is there a relationship between v2 and v1, do you think? The velocity of the flow at the bottom versus the velocity of the flow at the top? Is there any relationship between v1 and v2? If it's an incompressible fluid? The continuity equation, exactly. So we know that A1 V1 is equal to A2 V2, which means that we can eliminate V1 if we want to by doing this. And that's exactly what we're going to do. We're running out of time, so I'm going to do this relatively quickly. You'd have P naught minus P atmosphere plus rho G. Y1 was H, right? So we'll just put H in here. Call this H. And then for the other pieces, we've got 1/2 rho, and then we're going to have V2 squared minus V1 squared, and V1 squared is going to be A2 squared over A1 squared times V2 squared. And if we simplify all of this, I believe this is what you're going to get. I've skipped a lot of steps. I mean, not a lot, but I suspect that you can probably figure out how I got from this line to this line. I'm just going to look at it and make sure it looks right to me. Yell out something in chat if you notice an error, but I'm pretty sure it's correct. I'm pretty sure that it is correct. Okay, we're just going to have to leave it there. We're out of time, and I'm sure a lot of people have to get to other classes, so we'll just have to stop there and pick this topic up next time. We will have one more problem that I'll do with this, and yeah. Anyone have any questions? It's the end of today's lecture. I'll stick around and answer questions. Notice that in this equation, if A1 is significantly larger than A2, like, let's say, for example, that A1 was equal to, I don't know, maybe a meter. So let's say that R1 is 1 meter. Then this ratio is pretty much going to be 0. And then your answer would just be the numerator, which is what's going to happen a lot of the time. Like, if they don't give you A1, they just say A1 is really big relative to A2. What that means is that this term would drop to 0. Does that make sense? If A1 is significantly bigger than A2, this term will just be 0. And you're going to have to make that assumption a lot of the time. It's equivalent to making the assumption that V1 is 0. And you will have to make that assumption a lot of the time. If they do not tell you, okay, both of the cross-sectional areas, it's probably because they're going to want you to assume that one of them is much bigger than the other one, which is going to mean that you can negate or make negligible one of the velocities. Okay, we have to stop there. Thanks for showing up.